continue from our previous video. So we talked about in the previous lecture, we used the bootstrap using one sample data to estimate the range of the population mean. So that's why here we show you from the bootstrap, we have only one sample data. Then we resample 3,000 times. Then under 95% confidence interval. So that's in the baby weight example. We have the estimation under 95% confidence interval. That's our range for our population mean for the mom's age. Okay, so here is the maternal age. So that will be between 29.91 and 27.57, about like that. So that's what we have before using bootstrap. So we have one sample data, one set of sample data. Then we do the resample and find the average, find the range for the population mean. So in this week lecture, we talk about central limit theorem. So this central limit theorem, as we proved to you earlier, when we construct the distribution of the sample average, so then we have the center is population average. Then within two standard deviation, that will be 95% confidence interval. So then we can calculate standard deviation as well by using the standard deviation of the population mean equal to population SD divided by the sample size square root. So this one will be the same because the distance between population average will be the same as the population average to the sample average. So that's on the other hand, when we want to estimate the population average, we just need to find the standard deviation with the range from our sample mean. So that's why now go back to see our demo, how we use the central limit theorem to estimate the population mean. So the first thing, the same, we're using the same sample data. So that's find the sample data is our age, or the maternal age. So then we can get the sample size, then we can get the sample mean. And also we can find the sample standard deviation. That's all the data we can use in our NumPy function to calculate. So that's we get the information. So that's we can see our sample size is 1174. Then the average, sample average is 27.2282. Then the sample standard deviation will be 5.815. So now how we estimate the population mean? Right, so remember now, so population mean actually will from our sample mean plus minus to the standard deviation of the sample mean. So then sample mean here, so then the standard deviation of the sample average is equal to the population standard deviation divided by the sample size squared. Then you will say, we don't know the population standard deviation. But do you remember before when we talked about the three different standard deviation? Actually, any random sample, their sample standard deviation will be similar to the population standard deviation. So that's why here the population standard deviation, we were just using the standard deviation from the sample to plug in. Good. So that's why here you go back to see here, in order to get the standard deviation, so then we're just using the population standard deviation replaced by the sample standard deviation divided by sample size square root. Okay, so that's why here we will get our estimated standard deviation of the sample average equal to the sample standard deviation divided by the sample size, take square root. So that's we get. So this one is the standard deviation of the sample average. So our population average will be between the sample average plus 2 times the standard deviation and minus 2 times standard deviation. So here will be the, since we want to construct 95% confidence interval for the population mean. So that's why the left side is using the sample average minus the 2 estimate standard deviation of the sample average. So the right side will be the sample average times 2 times standard deviation. So that's our result. And also this result, because we applied the central limit theorem, all the sample, and also we only have one sample data. We only just direct to use the sample data size, sample data average, and the sample data standard deviation. So that's why this value will be the same for everyone applied the central limit theorem. So compare with this value from our bootstrap. Wow, so you can see actually pretty close, right? So the right side will be 27.56. We round up to 57, so they are the same. Then the left side will be a little different, but that's the 26.93, 91, and this one is 23.89. So only just like 0.02 different. And also one thing like we say, using the central limit theorem, we just according to the sample data you use. So if everyone use the same sample data, your estimation interval will be the same for everyone. However, for the bootstrap we also using one sample. We only have one sample data. However, since this sample data you will resample many times, you randomly select that with replacement. So that's why every time you resample, every time you run the bootstrap, they will have slightly different result. So that's why this result for example, everyone in the class, we apply this sample data, we run 3,000 times, your interval for your population mean will be slightly different. Okay, so that's our estimation for the population mean using our central limit theorem. Definitely run this lecture file and discuss with your classmates and compare your result. Okay, so we're done for the confidence interval and the sample, how to construct the 95% confidence interval to estimate the population mean. So let's move to the next topic. So the next topic we want to talk about is the sample proportions. What is sample proportion? So this what is sample proportions? So this sample proportion we will apply on the categorical data. For example, our outcome can be red or blue. Okay, so this one only have 2 categorical data. Or it will be yes or no result. They either vote for the candidate or not vote for the candidate. So that's our sample proportion. So if we use this sample proportion, so the average for this sample proportion will be our population average. So we see, for example, if we have the data, like earlier we say, that's for the categorical data, and we only have 2 results. So that's why you either 0 or 1. So if we have the data is 10, size is 10. So here we have 4, 1, and 6, 0. So that means the total for our sample is 4. So then the average is what? So 4 divided by, since we have 10 data, sample size is 10. So then we divide by 10. So then we got a 0.4. So actually this 0.4 and also is the proportion of ones, right? So that's why if the population consists only 1 or 0, on the other hand, that means the categorical data you try to analyze, they only have 2 categories. They either true or false, right? So as long as you have 2 results, we can just say they are true or false. So for this kind of answer, then the population average is the proportion of the ones in the population, because the true is 1, then false is 0. So then the sample average is also the proportion of 1 in the sample. So that we call proportion are also the average. For this kind of sample data, how they will affect us? Because if we want to use this sample proportion to do the estimation, we still have our confidence interval, right? So that's why if we want to have the confidence interval is 95%. So the 95% confidence interval for the population proportion will be the sample proportion. Then the same thing, we go to the right, 2 standard deviation, to the left, 2 standard deviation of the sample proportion. That makes sense, right? And on the other hand, remember earlier we also say your standard deviation for the sample average will be 4 times standard deviation of the population divided by square root of the sample size. So that's why the total width of the 95% confidence interval for a population proportion will be the 4 times the standard deviation. So the narrower the interval is, of course, more precise our estimation will be. So now, if we want the total width of the interval to be no more than 1%. Okay, so remember you can see, let me see if we can see the picture. Yeah, we just say, for example, of course, this one is the sample average distribution, but the similar concept. If we can have our sample size is bigger, so then actually your bell will be narrower, right? So that's why here, back to our earlier question for our sample proportion. If we can have a large size of the sample size, so how large the sample size is, then we can have this, the bell curve is really narrow and the width within 1%. So that's the question we want to get. So that's why that means this 4 standard deviation will be less than or equal to 1%. Right? So that's why we can write this formula. Okay, we can write this equation. So of course you can do greater or less than, but now since we just want to find the 1% boundary, so then we're just using the equal. So that means the 4 standard deviation will be equal to 1%. So then we just need to, since we want to find the sample size, right? So we move the sample size to the left-hand side. So then we have the 0.1% to the right. So then, of course, in order to find the sample size, we just need to take the square of this 4 times standard deviation of the 0,1 population, then divide by 0.01. So what is the sample size? Right, so the question for us is, what is the standard deviation for the 0,1 population? So let's see this one in our demo. Okay, so in this demo, actually we want to show you the standard deviation for any 0,1 population. So now we just assume we have one population size, only 10. Then we have only 2, 1. Okay, remember we only have 1 and 0, right? So we just said in this size of 10 population, we only have 2 1 That means the rest of that will be 0, right? Good. So that's why we create a 0, 1 population. We add 2 1, then the rest of that is 0. Then from here, can I find the standard deviation from this 0, 1 population? Yes, I can. I just passed that. Okay, so then we run to the 2 decimal place. So then you will see here, in this only 2, 1, and the rest of it is 0 population, the standard deviation is 0.4. Good. So on the other hand, here I want to show you. Then, since we have the 2, sorry, I kind of out of the 15-minute boundary. So let me show you this one. So then the next video, we will show you how to find all the combination for the 0, 1 population.